Okay, we're recording. So last time we were talking about graphs and level sets and such. And so I want to show you some relationships between them. For one thing, every graph is a level set. Now, that is seemingly a surprising thing to say given how much discussion I gave to how they're very different constructions, right? So importantly, while every graph is a level set, it's a level set of a different function, right? So actually not that surprising. So here's the big idea. Suppose you're looking at a graph of some function f. Now, let's be careful about what we mean by this. So f is a function with, let's say, n input variables and one output variable. And when we say graph, of course, let's not forget what graph means. Graph means that we're setting the values of that function equal to a new variable that I'm going to call y. All right, so the function we're taking the graph of is f, and the graph is described by setting its values equal to 1. Okay, all right, so there you go. Now so we have an equation then that describes our graph. And of course, I can manipulate that equation around a little bit as follows here. It's not a particularly challenging little bit of algebra. Practically nothing happened. I took the right side of the equation and I subtracted it over to the left side of the equation. But now look and notice that this is now looking like a level set. It is written as something equals a constant. Happens to be 0. Fine. But that makes it a level set, right? By virtue of something being set equal to a constant, we're looking at a level set. And specifically, we're looking at a level set of now this function, which you'll notice is not the same function as f, right? The function whose graph we were looking at was f. It had n input variables. The function whose level set we're looking at, well, you can look at this expression. This thing that we're setting equal to 0 is an expression that involves n plus 1 variables, right? It involves x1 through xn, yeah, sure, but also it involves y, put together in this very specific way. So this is both a proof and a kind of a formula. This is a proof of my claim that every graph is a level set, and it's a formula for the function whose level set is that given graph. All right. Okay, so now why would we ever care about such a thing? Sometimes it may be that you're looking at some sort of a surface or what have you that is given as a graph. Right? It may be specifically, suppose we're interested in the graph of the following function, blah, blah, blah. And the question that you might be facing could be something which, the calculus of level sets would be really convenient. The calculus of level sets, which we'll be learning over the next few weeks, could be exactly what you need to give you exactly what you want. And so taking something given as a graph and reconceiving of it as a level set like I did here. And notice how the algebra is trivial. The algebra is not the point. It's the proper interpretations of the language and the proper interpretations of the algebra, right? This little little bit of algebra tells you what function to play with if you want to use the calculus of level sets. It's not the original function. It's this new function. Let's see an example of this in action. Here we have a function of which we're going to look at a graph. Again, graph, keep in mind, graph means we're going to set equal to a new variable. So here we have explicitly the graph of that function, x squared plus y squared. Everybody with me so far? Here's the trivial but critical algebra right there. Right, write down the equivalent, but importantly, differently understood algebra down here. And sure enough, we're looking at a level set, right? Something equals a constant. The function we're looking at a level set of is this thing right here. It's a function of x, y, and z. And it, again, very importantly, not the same formula as f. Is everybody happy? Okay. Tragically, it doesn't go the other way around. Wouldn't it be nice if every time you had a graph, you can view it as a level set, and every time you have a level set, you can view it as a graph? It's just not true. Not every level set is a graph. And this is an easy counterexample. I mean, there's a level set. You can, again, to give away that it's a level set is that you have something equal to a constant. So this is written as a level set. We're looking at a level set then of this function, x squared plus y squared. This is an easy equation, right? X squared plus y squared equals 1, no problem. And you can't view this as a graph. It just doesn't work. Keep in mind, if you're looking at a graph, it would have to pass the vertical line test. This fails the vertical line test, not only sometimes, but in fact, almost everywhere. Right? Fails the vertical line test. Another way to say this is you cannot solve for either x or y. And now I emphasize here when I say solve, I mean solve uniquely. In other words, there is no way to turn this into x equals function, namely one value, right? Just can't do it. There's always the possibility. Well, it could be the plus or it could be the minus when you take the square root. So, losing. How we doing? Okay, so this is a one-way convenience. Every graph is a level set, and not the opposite. Okay, so now we're going to get into understanding equations. There's a couple of tricks that I have that I think are worth knowing for how to deal with an equation of 3 variables. We're going to deal with a lot of equations of 3 variables in this class. No surprise there, I'm sure. And so what do you do if you have an equation of 3 variables? How do you know what that surface looks like? So first, a really handy trick that I like to call rotations. So specifically, if a certain thing happens, if your equation involves x's and y's only, very importantly, only as part of this expression right there, square root of x squared plus y squared. If that is the only way that x and y show up in your equation, then we get a very powerful conclusion. Your surface is rotationally symmetric around the z-axis. And that is a tremendous amount of geometric information, as we'll see in an example that's to follow in just a minute. So what I love about this observation is that this part is really easy to check. It's just a casual observation. Just look for the x's and y's. Do they, in fact, only appear as part of that expression? Super easy to check, and then powerful result. Okay, now why does this work? So let's consider the following scenario. Got a point there, and now let's imagine what happens when I rotate it around the z-axis, and among other things, I will get this point over here. Now these 2 points have different x's and y's. Right? These are very importantly different points, and so you wouldn't think just, you take a couple of points that, they're different coordinates. You wouldn't think you could plug them into the same equation and they would just always they would always be together. They either both work or they neither work. What are the odds? They're different points, right? But because of this rotation, the distance to the z-axis for the first point and the distance to the z-axis for the second point, same distance. It's a rotation around the z-axis. So those distances are the same, which means that square root of x squared plus y squared for these 2 points, same. And that's the only way that x and y show up in this equation. Right, now furthermore, because these points are rotations of each other, they also have the same z coordinate. So, again, this equation, x's and y's only appear in this form where the 2 points agree. And of course the equation can also involve z, but they agree on z also. So even though they have different x's and y's, these 2 points are going to agree on everything related to the actual equation you're plugging in for. So these 2 points, either they both work or they neither work. Does that make sense? And another way to think about this is that means that this surface must be rotationally symmetric around the z-axis. Questions? All right, now here's a different point of view. Same result, different point of view. If x and y appear only as part of this expression again, let's think about what would happen if I converted this into cylindrical coordinates. Right? How do you convert an equation into cylindrical coordinates? Well, everywhere you see x, you put r cosine theta instead. Everywhere you see y, you put r sine theta instead. But there's various other conveniences, and one of the convenient tricks is everywhere you see square root of x squared plus y squared, you just put r. So if this is the only way that x and y show up, then, well, wherever I see x or y, I'm also going to be seeing exactly this, which I can just rewrite as r. The only other variables left in the equation are z. Z is a cylindrical coordinate too, so I just leave the z's, and no thetas would have showed up. Right? And, well, if your cylindrical equation doesn't have any thetas in it, well, no thetas means that all of the theta cross sections look identical. We saw an example of this previously, and with all of the theta cross sections all look exactly the same, that means that this surface is rotationally symmetric. So, same conclusion by way of a different argument. So whichever one of those you like better. Feel free to use either one of those. Okay, here's how you're actually going to use this in practice, though. In practice, you're going to capitalize on the fact that if you have such a surface, then you can look at any cross-section. That is, any cross-section in any plane containing the z-axis, and then just rotate it. Right? This is a neat fact about rotationally symmetric surfaces. If it is indeed rotationally symmetric, then it is a rotation of, take your pick, any such cross-section. So here's an example of using that. Let's try to understand this surface right here. Reminder, we saw this surface previously, and I made the hand-wavy argument about how, well, it's vaguely parabolic in the x direction, and it's vaguely parabolic in the y direction. It's kind of hand-wavy. Now we're going to crush this, because step one, x and y appear only in the given form, and so this is rotationally symmetric. If you're worried about the lack of the square root, notice that I can rewrite this equation as z equals square root of x squared plus y squared squared. And now x and y appear only in the proper form. So another way to say this is you don't need to worry about it if the square root's missing. Okay, so rotationally symmetric surface, that means I can understand this surface just by looking at any cross-section at all. Let's see here, rotationally symmetric around the z-axis. So I'm going to pick now this plane right here, the YZ plane, and look only at that cross-section in that YZ plane. Notice this YZ plane does contain the z-axis. Again, that's part of the deal. You have to look at cross-sections that contain your axis. Okay, in that cross-section, x is equal to 0. I can plug that right on into the equation. The equation then turns into this, just z equals y squared, and that's just a parabola, high school algebra. All right, now let me pause and make sure everybody's still on board. Right, we're looking in this cross-section in the YZ plane. The YZ plane has x equal to 0. So if I'm only interested in what's happening in that YZ plane, I'm allowed to plug in x equals 0, boom, boom, and now we have just a parabola, thus that. And it's kind of all over but the shouting at this point. We already know that our thing is rotationally symmetric, and so I can then just rotate that cross-section, and when you rotate that cross-section, you get this shape that I had previously kind of hand-wavingly argued is what the graph should look like. What do you think? Everybody follow it? Nice little 3-step process there. Okay, so this, and then a little terminology. This thing here is called a paraboloid. I think the motivation for the name there is pretty clear. You can see the root parabola in there, and paraboloid is just their way of saying that it's a surface that derives out of a parabola. Okay. All right, another example. How would I understand this surface described by that equation? So, same strategy. Notice that again, I'm picking and choosing carefully. I've got a surface here that x and y appear only in the proper form, right? And again, only in that proper form. It's not good enough that it appears in that proper form among other appearances, right? There cannot be any sort of extraneous appearances of x and y. Okay, so rotationally symmetric around the z-axis. That means I can look at any cross section that contains the z-axis. Take your pick. Last time I was in this situation, I picked the YZ plane. This time, just to show I can, I'm going to pick the XZ plane. It doesn't matter. Any cross section will do. Okay, so this cross section, the XZ plane, has y equal to 0, which I can toss into the equation, and tossing that into there, this equation turns into that equation, which of course we recognize as a hyperbola. And now I'm aware of the fact that high school algebra was a long time ago, right? And parabolas, there's always this question: which way does it go? Is it like this, or is it kind of the other way? It's really easy to get that backwards. Right, so refresh yourself, please. However you prefer to think about this, there's different ways to think about it. But dust off your old algebra notes from high school. Make sure that you're proficient with getting that right. It's going to come up. By the way, if you're a little shaky on this, and if you really don't know how to straighten that out in your mind, come to office hours. I'll be very happy to explain. No big deal. But one way or the other, make sure that you polish that off. So again, we have a cross section. Again, we're just going to rotate the cross section around the relevant axis, and when you rotate that purple curve, I appeal to your geometric imagination. And it makes this whatever that thing there is. Yeah. What do you think? Is everybody happy? Is everybody following me? Good deal. Okay, a little bit of terminology. This is called a hyperboloid of one sheet. And there is another kind of hyperboloid that we're going to see in a few minutes. Okay. So, now, up to now, we've been doing all of our rotations around the z-axis. We've been using this theorem here, which is about rotational symmetry, only around the z-axis, and only because x and y appear in this form. And it's because x and y appear in that form that the axis is the z-axis. So, picture and argument, etc. Now, I claim, though, that there are analogous results, analogous theorems that you can state about rotational symmetry around the x-axis, rotational symmetry around the y-axis. And by sort of pattern recognition, you could probably guess what those statements are. That said, I do think it's a healthy exercise to think through the argument. So, where did I write that down? I guess I wrote can be made. So I want to encourage y'all to do this, to make the argument for similar results about rotations around the other axes. And I'm just going to proceed to use these similar results. In this example here, we're going to try to understand this thing, whatever that thing is. This equation subsurface. And do x and y appear only in the proper form? Well, no. Doggone it, there's a minus sign in there that's messing things up. And this theorem is extremely rigid. even though it's real close. All right, we're just a minus sign off. No go, and any claims about rotational symmetry around the z-axis, absolute crash and burn, does not work. Okay. So notice, though, I can rewrite this algebra as that, and I can notice that y and z appear only in what you might call, their version of this previously discussed proper form. And per theorems that y'all are going to think through by analogy to the arguments we've already made, this is therefore rotationally symmetric around the x-axis. And so I've got a axis of rotation there that is the x-axis. How are we doing? You believe it? Everybody's happy? Okay, so we're rotationally symmetric around the x-axis. That means I can, again, pick any plane that I want that contains the x-axis. Now, I'm going to pick here the xy plane just to mix it up, right? It doesn't matter. I can pick any other plane that I might want as long as it contains the x-axis. So, for example, I could pick the xz plane if I wanted to. Whatever. Right? And if you're a masochist, you could pick some angled plane like this. I don't advise it. But there is an argument that could be made there. But why would we? Why would we make our lives unnecessarily confusing? Nice, easy choices. Pick a coordinate plane. Here we're going to use the xy plane where z is equal to 0. If z is equal to 0, then that makes this equation turn into this. This is an easy equation. Again, this is one of these hyperbolas that you all remember from high school algebra. And again, make sure you can get it straight and get it oriented the correct direction. But that's the resulting hyperbola. So this is what the given cross section looks like. And knowing that that's the cross section and knowing that the result is rotationally symmetric, then I get my result by rotating this cross section around the x-axis, and that results in, well, it's kind of a weird picture. So you look at this hyperbola, and in some sense they don't, like I'm rotating around a fundamentally different axis. They don't rotate into each other. They kind of rotate parallel to each other in some sense, right? And so you get this picture here where you have I like to think of this as being a contact lens. I don't know. That's just what I see when I look at that thing. And so as a whole, then, I feel like this is that's what I like to call the staring contest. So two eyeballs that are just pointing right at each other. If you were looking for something that this reminds you of, that's what this reminds me of. But the proper name for this is a hyperboloid of two sheets. And I think that terminology, easy to motivate. Again, we're rotating a hyperbola, thus hyperboloid, and two sheets because there's two connected or disconnected components, I guess you might say. So thus the distinct clarification from the hyperboloid of one sheet, right, like that right there. Okay, everybody good? Is everybody happy? Okay, now another little bit of algebra, sort of an algebraic trick that I think is extremely useful. Very often you're going to find yourselves looking at an equation such as this one that you haven't seen before. And yet, even though you haven't seen this before and technically you don't know what this thing looks like, yeah, but it looks really, really similar to another equation that maybe you have seen before, where maybe you have a pre-existing answer for what it looks like. Take this green equation, for example. This is just rho equals 13. This is very clearly a sphere, right? No problem about seeing that this is a sphere. So I've got an equation that I understand that isn't actually what I'm interested in. I'm interested in something that looks, very close, not quite, but very similar looking, right? And the question is, if I can identify, for example, that I've just, replaced all the z's with two z's, like that. And if I can figure out what this process does, the process of, you replace every z with 2z, like I did here. Every z turns into 2z. If I can figure out what this algebraic process does effectively to the resulting surface, then I can use my knowledge of my starter surface to help me figure out the answer to my actual surface of interest. The equation of interest, what is that resulting surface? Everybody see the big picture strategy that we're going to try to fill in here? Okay, so I'm going to kind of argue by example here, but I think it's pretty plausible. Let's think about, let's say, this point right here. 3, 4, 12. You can confirm for yourselves that works in that equation. So we have a point on our sphere. Doesn't work in that equation. Well, of course not. Of course it doesn't work in this equation. It's a different equation. It worked in this equation, but then I fiddled with the equation. In a different equation, you shouldn't expect that this would work. Now let's analyze exactly, precisely, specifically why it didn't work. And it didn't work because this 12 right here, that works when it goes into that spot, right? Well, it goes into that spot where it was supposed to be squared. So the 12 is the thing that's supposed to get squared. If you try to put this 12 here into there, it doesn't just get squared. It gets multiplied by 2 first because I replaced all my z's with 2z's. And so it gets multiplied by 2 before being squared. And obviously that screws it all up. Okay. So here's the clever idea, though. The clever idea is to say, well, yeah, 12 doesn't work because of the whole multiplying by 2 thing. But what if I were to put a 6 into there for z? If I put a 6 in there, well, 6 is going to take that extra multiplication by 2 and turn into 12, which gets squared just like this 12 got squared, and everything works. So this point does work. 3, 4, 6. So what I'm going to say happened here, and this is just a point of view, what I'm going to say happened is that the process, the algebraic process of replacing the z's with 2z's caused this point, 3, 4, 12, to get its z-coordinate cut in half effectively. Right? 3, 4, 12, that used to work in the old equation, well, now it's sort of, it's 3, 4, 6 that works in the new equation. So, roughly speaking then, what you do to the algebra, I replaced the z with 2z. This multiplication by 2 here effectively causes in the solutions, namely to the surface, that the z-coordinates all get cut in half. And I like to think of that as kind of a squishing of the surface. Right? So this resulting surface down here is what you get when you take your original sphere and squish it by a factor of 2 vertically, thus giving you this ellipsoid thing. Okay. So this is an example of what I claim holds in general, that roughly speaking, what you do to a variable in equation, the opposite happens to the surface. This extra factor of 2 effectively divides solution coordinates by 2. Everybody on board? Believable? Okay. Yeah.
So, like, if you make changes to multiple variables in that same sense, do they compound in that way?
You got to do it. Take it one step at a time. But yeah, roughly speaking, yeah, absolutely. But you do have to be careful to only take one step at a time, because it can matter which order you do it in, and yeah. So there's harder examples that have that happen. Yeah. Okay. All right. So let's see more examples of this. We have here again a shape that we recognize. All right, so we already know what that one is. And we can use that as a sort of a launching point to try to figure out what's the deal with this equation. How do I understand that equation? Well, it's not the same. It's very importantly different, right? But you can think of this new equation as being the result of replacing all the x's with x over a, then replacing all of the y's with y over b, and then replacing all of the z's. Oh, come on. Let's try that again. Replacing all of the z's with z over c. So there's kind of three things that have happened, and these are all in different directions, and so it doesn't really matter what order you do these in. I'm going to kind of do them all at once. But as a result of replacing x with x divided by a, the opposite of dividing by a would be multiplying by a. And you'll notice that the result is that this has been stretched in the x direction by a factor of a. Right? This intersection on the positive part of the x-axis, this originally was a unit sphere that used to be at 1. And now, because of stretching by a factor of a, now it's at a instead of 1. And you can just plug that point into the equation and confirm that sure enough it works. Okay. Likewise, stretching by a factor of b in the y direction. Let's see here. Let me go ahead and stretching by a factor of b in the y direction, stretching by a factor of c in the z direction. All right. Couple other examples. I'm going to be quick about these because they're all kind of morally the same as things that we've seen. We've already understood this paraboloid, right? Rotationally symmetric. And I can then think, all right, well, apparently I'm replacing x with x over a, and apparently I am replacing y with y over b. And so that means that this thing here must be the result of this is what you get when you take your existing paraboloid and you apparently stretch by a factor of a in the x direction, and you stretch by a factor of b in the y direction, and that's going to take your original paraboloid that has circular cross sections, and by stretching it by these different amounts, it's going to stretch out those circular cross sections into elliptical cross sections, and so we call this an elliptical paraboloid. Everybody with me? Yeah. Okay. So, by the way, I'll point out that good that we had this tool available, because while we were able to make a rotation argument for this one, you cannot make a rotation argument here because A and B are different, presumably, and X and Y just don't appear exclusively in the required proper form, so there is no rotational argument that you can make at all for this surface, right? So this idea of deforming things allows you to take an easier question that is susceptible to a rotation argument and then benefit from that in trying to understand one that is not eligible for a rotation argument. Okay. Likewise, hyperboloid of two sheets. We already studied this one. Various replacements. Big surprise. This kind of stretches things out in various amounts in various directions, and you get a elliptical hyperboloid of two sheets. Okay. Various other examples in the book. I'm going to let y'all read. How we doing? Is everybody all right? Okay. All righty. Moving along. So we're skipping section 2.2. You may have noticed this on the content syllabus. Section 2.2 is not there. That's another one of these tough choices. There is a point of view that says that 2.2 is really important. It's about limits. If you think about it, let's dial back to single variable calculus. The big ideas of single variable calculus, derivatives and integrals. If you look at the definition of derivatives and integrals, derivatives defined with limits. Integrals defined with limits, right? So in fact, very strong case can be made that the fundamental idea, the cornerstone concept of all of calculus is limits. So, and yet we're skipping the section on limits. So the reason we're doing that is because what we really need limits for is what I'm going to call mathematical rigor. And this course is far more about, let's get to the results and let's do applications and let's understand things geometrically and conceptually, etc. And yes, we're going to compute lots and lots of stuff. But the proof aspect of things, not really what this course is about. Primarily, a little bit, but just not primarily. And so we just don't have, I'm going to say, time in the schedule. Again, with the tough choices that have to get made, 2.2 just didn't quite make the cut. And it makes me a little sad, but, my loss is your gain, something to that effect, right? And so anyway, you're not responsible for 2.2. And we move on now to 2.3. Okay, so this is about the derivative. The derivative of a multivariable function is a much more complicated discussion than it is in single variable calculus. In single variable, there is the derivative. That's it. There's only one derivative, therefore it's the derivative. In multivariable, there are lots of kinds of derivatives. There's a bunch of them, and they're importantly different from each other. They have various things in common, and there's various connections and relationships, but they are different things. So how we use the word derivative to apply to all of them, even though they're different, is the fact that they have this one thing in common. This is just the way I like to say it, but derivatives all relate input changes to output changes. Now, there's a bunch of different kinds of derivatives that we're going to talk about. They will all, in their different ways, relate input changes to output changes. All right. We're going to start with partial derivatives for a combination of reasons. Here are my take on the three reasons. We're going to start with this. They're easy to compute. We're going to see that very quickly. They are super easy to compute. That's a good thing. All right, this is valuable. They are familiar in the sense that they're going to, in a very natural way, really remind us of single variable derivatives. In a way, they kind of are single variable derivatives. But anyway, they're very closely relatable to stuff you already know. And so it's a nice sort of easy first step, a first conceptual step. So that's nice. Then a pretty important additional point, the book starts with partial derivatives. And I don't want to say that ties my hands. I've diverged from the book more than once in the past, and in some ways I do in this class, but not in this way. The book does it. It makes it very natural for us to just kind of follow along the same way the book does it. Okay, so that said, note absent from this list is any claim that it is in fact mathematically natural to start with partial derivatives. And I would make the hot take that it's not actually mathematically natural to start with partial derivatives. When y'all leave this class, one of my big hopes is that you will not think of partial derivatives as being fundamentally cornerstone, what is a derivative. There is a different thing that we will get to later, possibly Wednesday, I hope, that I think should be the thing that you call the derivative. So this is a ultimately natural first step, but we're going to soon see that there's a much better thing that we could do instead. So anyway, please do not hang your hat on partial derivatives as being the cornerstone idea of multivariable derivatives. They're really not. Okay, so anyway, here's how you compute them. This is kind of arbitrary seeming, but ultimately it's going to be really convenient. We're going to choose to just decide that we're going to pretend that most of the variables are constants. And we're making that up, right? This is a choice. That's pretty sketchy as a choice, by the way, if you think about it. We're just going to pretend that these things that are not constant, we're going to pretend that they are. Right? So we're going to have to come back and address that. But that said, let's just, for the moment, let's pretend that most of the variables are constant, except for one of them. And let's say the ith variable, x sub I. Let's suppose that one we're going to leave as a variable. Well, if you think about it, if we have a function of several variables, but we nail down the values of all but one variable, treat them as constants. Well, you had n variables, but now all but one of them are constants. So now we really only have actually a single variable function. If you think about it, right? All the others are constants. Is that cool? Is everybody with me so far? These are arbitrary choices. And again, we have to deal with the consequences of these arbitrary choices. But nevertheless, we've turned a multivariable function into a single variable function. And once you have a single variable function, just take the usual derivative of that single variable function. This is what a partial derivative is. And let's see that in action. Well, let's talk notation first. So here's the notation for partial derivatives. You'll notice that this notation involves a new symbol that is not a D. Very importantly, not a D. If you write D instead, it's wrong. This is not a sort of optional thing. It's importantly different from a D. And then likewise, it also kind of looks like a lowercase Greek letter delta. It's very importantly not a lowercase Greek letter delta. So it may be that this is your first time to encounter this symbol, and if so, it might be a prudent idea to do what I did when I was y'all's age, or when seeing this material for the first time. And then as I got out a scrap sheet of paper, and I just kind of practiced, trying to make that symbol. Because, well, it's a new symbol, and you need to be able to write it and have it interpretable every time. So, anyway. Okay, so there it is. Now, of course, no surprise. You can kind of take this the thing and kind of put it out front. We've been doing that kind of thing with single variable derivatives for a long time. Then there's kind of a Newton-like notation. Y'all remember, I'm sure, that if you have df dx, a single variable derivative, this very often gets written as f prime. And in the same way that this is kind of analogous to that, kinda, right? What would be analogous to Newton's notation? What would be analogous to f prime? You can't just write f prime. There's a bunch of different variables that I could have decided to be the one that is serving as the actual variable. So instead of saying prime, we just make a subscript indicating which variable it is that we're taking the prime with respect to. And so this is kind of what I would call the Newton-like alternative for partial derivative. Okay. All right, now let's compute. Okay. All right, our first partial derivative computation. And this looks pretty scary at a glance, right? You see there's a product of three factors. One of them is a cotangent, which is annoying. Oh gosh, I remember all those formulas for derivatives of obscure trig functions. That's, something you'd be worried about. Then you realize that furthermore there's a composition involved, and there's a product inside, and there's an exponential inside of the product, and ugly, right? So this could take a lot of space, one might worry. But remember, you're going to hold all the variables constant except for one. All of the other variables constants. Right? So when we're saying that we're taking the partial here with respect to y, that means that y is a variable. That means that y squared is a variable, but everything else is constant. So x is a constant. That means e to the x is a constant. X is a constant means x squared is a constant. Z is a constant means e to the z is a constant. That means the product is a constant. The cotangent is a constant. So most of the ugly in this equation is just ugly constant. And ugly constants are constants. And when you're taking a derivative, remember step 2 in the process is to take the derivative in the usual way, right? The derivative of y squared is 2y. And any multiplicative constants, any, constant factors, well, they just come along for the ride. Just just treat it like it was a k or something like that. So, all of this just stays there. Nothing happens to it. Oh, I'm sorry. I should have done that in gray because they're constants. Sorry. There we go. Constants. How we doing? Everybody happy? Yeah, so pretty easy in this case after all. It looked like it was going to be horrendous, but most of it was constant, and the remaining derivative of y squared, 2y, was a really easy derivative as it turned out. Okay, more examples of this. Here's another one. This one looks a little scary because we've got a function to the power of a function, so it seems. Right? But in fact, keep in mind, you got to look very carefully. We're taking a partial with respect to x, and that means that y is a constant, which means that y squared is a constant. And when you have a constant exponent, well, you bring down the exponent and you subtract 1 in the exponent. And the usual power rule, right? Because it's a constant. And then all you have to do is just, in addition to the power rule, don't forget the chain rule. And boom, there you go. Actually pretty easy to do. How are we doing? Is everybody all right? Okay. Likewise here, let's take this thing. Again, looks like function to the power of function. Scary. But z partial, so z is our variable. That means that x and y are constants, which means that this whole thing here is a constant. You could read this effectively as k to the power of z. As far as this partial is concerned, I've got k to the power of z, and there's an old single variable calculus formula that the derivative is then k to the power of z times and then the natural log of that constant k. So, old formulas. Okay, is everybody happy? Okay, so I make the case that partial derivatives are the easiest derivatives to compute, because it's just like doing single variable derivatives, which would have been most people's nomination for the easiest derivatives to compute, just like single variable, except you get to pretend that large chunks of your function are constant, which makes it easier by quite a bit. So, world's easiest derivatives to compute. That makes for a good stopping point. We'll end it right there. And good to see y'all again. Hope everybody had a good weekend. See you on Wednesday. And as usual, if you came in after I did attendance, make sure that I mark you down.